Welcome to Lecture 8 of the design of seismic resistant RCC residential building based on IS code. In this Lecture 8, we will see how column is designed in ETABS. We will see the result that we obtain for the design process from ETABS, and then we will look at some aspect of the design, how ETABS performs the design of column. In this lecture, we will only look at the moment design, that is, we will look at the shear force design or the design for shear capacity in the next lecture. So only half of design of column will be covered in this lecture course. Before starting with my presentation, let us go to ETABS first. Okay, this is the result of design. Currently we are being displayed, or the software is displaying us longitudinal reinforcement for columns and beams. We did up to this design process in our previous lecture. Now we will take one sample column and we will see at the design of that column. Before doing that, what I did during this design later was that I changed the cross section of columns, because if you can remember, during our previous lecture we were getting only the minimum reinforcement for columns. So we began our design of this structure from preliminary design, and in preliminary design we took a cross section of size 400 mm by 400 mm for columns, and after designing we saw that only minimum reinforcement percentage was being displayed for those columns. So I decreased the size of the columns to make the design more optimized. What I did for that was I unlocked the model, and then let me show this again. I unlocked the model. I went to define section properties, frame sections. Previously there was column 400 by 400, now we have column 350 by 350. So I selected that column 400 by 400. I went to modify show property and I changed the depth and width of those columns, and I renamed that column again. So the process is very easy. We just have to go to the definition menu and we have to change the section dimensions for the column. And after changing the section dimension, I run the analysis again and then I perform the design. Once after you change that dimension or section dimension, you again have to perform some checks for the building. Because we have decreased the column size, it causes decrease in the lateral stiffness of the column also. So we have to check for the deflection of stories. We have to check for torsion also if there is any significant difference between our previous checks and our new checks. So now I perform the concrete frame design. Now our design has been performed. Now I want to select one sample column and see how it is designed in ETABS. For that, I have selected this column at grid B5. This column. If you right click on this, you will see the design results. You will see that 0.9 dead load minus 1.5 earthquake load is the governing load combination here. We are getting longitudinal reinforcement 990 and major and minor reinforcement 387.95. So how do we get to 990? If we click on this menu details, then you will see the various design that ETABS has performed, and from this design you get the rebar percentage 0.81 or 990 mm square area. So how is this design performed? Let's see that in today's lecture. So I'll go to my presentation and design of column. I have taken these points once again from the concrete frame design manual of CSI itself. And this concrete frame design manual is based on the IS 456. What does it say? The design procedure for the reinforced concrete columns of the structure involves the following steps. There are major 3 steps in the design of concrete columns by ETABS. First, ETABS generates axial force biaxial moment interaction surfaces for all of the different concrete section types of the model. For reinforcement to be designed, the program generates the interaction surface for the range of allowable reinforcement, which is by default 0.8 to 6% for all types of concrete frames, IS 456-2000. This 0.8 to 6% is based on clause 26.5.3.1 of IS 456 code. So first, the software generates the interaction curve, or you may say because the software generates a 3D interaction curve, we get an interaction volume, and the 3 axes for that interaction volume or that interaction surfaces is axial force in one axis and biaxial moments, the moments in 2 different axes. We get a 3D interaction surfaces, and that 3D interaction surfaces are generated for all the allowable value of reinforcement, which is 0.8 to 6% for all types of concrete columns. And using that interaction curve, the software calculates the capacity ratio or the required reinforcing area for the factored axial force and biaxial or uniaxial bending moments obtained from each loading combination at each station of the column. Then the capacity ratio is calculated. This capacity ratio is calculated if the reinforcement in the column is to be checked. If the reinforcement is to be designed based on this interaction curve, the software gives us the value of reinforcement. But if we have already given the value of or the percentage of reinforcement at the beginning itself, and then we have to check that reinforcement value in ETABS, then the software gives us capacity ratio. And finally, the software designs the column shear reinforcement. So first, the software generates interaction curve. From that, it calculates capacity ratio or the value of longitudinal reinforcement, and then the software designs the column shear reinforcement. So let me talk a little about what is interaction surface. We have touched a little on this subject in our previous lecture also. I want to go through it once again. Let me draw a 2D interaction surface. Suppose this is x-axis and this is y-axis. In the x-axis, we have the uniaxial moment in case of 2D interaction surface, and in the y-axis we have the axial compressive force. So, but if you see it SP16, which is the standard procedures for SP16, it is a design aid for IS 456. You see that in our x-axis, what we have is MUY FCK BD square, and in the y-axis we have PU FCK BD. PU FCK BD. We have this in our SP16 design code, and our curves are somewhat like this. And we can divide this curve into 3 different sections by using this 2 line. One is this section, and one is this section, second is, and the third is this section. So let me call this 1, 2, and 3. This first section or this first region is known as the minimum eccentricity region. In this minimum eccentricity region, the columns are designed in which dominating force is axial load. We see that there is a high value of axial load in this region and a very little value of moment, or in this region, column is designed primarily for axial load, and we only consider the minimum moment that arises from the minimum eccentricity criteria. So the columns designed in this region will have minimum moment carrying capacity. We saw in the previous lecture that we had to consider the minimum eccentricity for the design of columns, which was given by minimum value of E is unsupported length of the column divided by 500 plus it is either B or D divided by 20 or 20 mm. So from this formula, if we get the eccentricity value to be less than 20 mm, then we have to take the minimum value of eccentricity as 20 mm. Otherwise, if we get the eccentricity greater than 20 mm from this formula, then we have to use that eccentricity. And using this minimum eccentricity, we design the column in this region 1 for minimum moment carrying capacity. So this is the minimum eccentricity region. Now this region 2 is known as the compression control region. So in this region, if the columns are designed in this region, then they are designed for both axial load and bending moment. That is, in this compression controlled region, both axial load and bending moment are dominating forces. Here bending may be either uniaxial or biaxial. So both axial forces and bending moment will be dominating. No tension occurs in the region due to bending. There is no tension in this region, hence it is called compression control region. And in this region we see that, let me draw this once again here. So in this second region is the axial load carrying capacity in y direction. We see that axial load capacity, if we travel from this point to this point here, the axial load carrying capacity decreases, but the bending moment carrying capacity increases. So in compression control region, both forces are dominating. Now this third section or third region is known as tension control region. In this tension control region, bending moment is the dominating force, and that bending moment causes tension in the section. Therefore, we do not want tension in our columns. Therefore, columns are not designed in this section. And in this section, as we increase the bending moment carrying capacity, we see that the curve is going towards the left hand side. So if we decrease the axial load carrying capacity, our moment carrying capacity is also decreased in this section. So columns are not designed in this section. So this is the general concept of interaction curve or interaction surfaces. And these curves are generated for various values of reinforcement percentage. As we talked about here, by default, the minimum value is 0.8% and 6% is the maximum reinforcement in concrete columns. So we generate this interaction curve for different values of reinforcement percentages. And from these curves itself, if the reinforcement in column is to be designed, then we determine the value of reinforcement required to resist that amount of axial load and bending moment. So this is the concept of interaction curve. So let us go through step by step for the design of columns. The first step is we determine the factored moments and forces, or the software determines the factored moment and forces. The loads for a particular design load combinations are obtained by multiplying the corresponding factors to all of the load cases PU, MU2 and MU3. Let's see here, this figure I generated from, or I took a screenshot of this figure from ETABS. When we right click on any column that has been designed and we click on details, then we get a form. And from that form, I chose a particular part for axial force and biaxial moment design, and I posted the screenshot here. This design PU kilonewton, design MU2 kilonewton meter, and design MU3 kilonewton meter. These three values we obtain from the governing load combination. That these three internal forces or these three design values are generated from the particular load combination that governs the design of those columns. So we get the value of PU, MU2 and MU3 from load combination. Now we talk that columns are designed for minimum eccentricity moment. Although we suppose that our axial force in column is acting concentrically at the center itself, there may be some displacement of this axial load. This may not act at the very center, but this may be displaced, or there may be minimum eccentricity due to various reasons. So we first calculate that minimum eccentricity that may occur in our columns, and then we also have to design for that minimum eccentricity. And that minimum eccentricity value is given by L by 500 plus D by 30, or L by 500 plus B by 30, subjected to a minimum eccentricity of 20 mm. So this we have in our IS 456 code clause 25.4. So now let us calculate minimum eccentricity. Our minimum eccentricity, first we have to calculate using this formula. Unsupported length, or the length of the column, divided by 500, which is 2850 by 500, plus D or B by 30. Since the value of D and B is the same, 350 by 30, we get the eccentricity to be 17.37. And another we have to check is 20 mm. We have to take the greater value of these two minimum eccentricities. So we take the minimum eccentricity value to be 20 mm. And as the software manual says that columns are designed for minimum eccentricity moment P into E minimum, when moment is less than P into E minimum. What is P here? 209.9053 kilonewton. So 209.9053 kilonewton into 0.02, this is 20 mm, we get 4.1981 kilonewton meter. So this, our minimum eccentricity is the same in both x and y direction. So our minimum moment due to eccentricity will also be the same, 4.1981 kilonewton meter, which we get here. 4.1981. And after finding all these values of minimum moment and design moment, the software calculates revar area and revar percentage from the interaction curve. This is how the software designs for column. So what the software does, if the design has to be checked, then the software calculates the moment capacity of those columns, which we have in number 2 now. Determine additional moment for column slenderness. So we saw that even for columns with uniaxial loading, there could be some additional moment due to minimum eccentricity, and we had to design for that minimum moment also. In the next case, some additional moments may be generated in the column due to column slenderness. So first we have to check whether the column is slender or not, and if the columns are slender, then we have to find the additional moment that may occur due to the slenderness property of column. Because if our column is not slender, or if our column is short, we assume that the column has the capacity to take full axial compressive load up to failure. That means the failure of short columns occur due to the crushing of the concrete under the effect of axial compressive force. But in case of slender columns, the column fails before reaching the full load capacity. The column fails in buckling before reaching the full yield or full load capacity. So in slender columns, we have the additional effect of some moments generated due to the slenderness property. We first have to check whether our columns are slender or not, and then we find the additional moments if the columns are slender, and that additional moments formula we have here, EMA2 and EMA3. These formulas is derived from IS 456 clause, these codes here, and various definitions of the symbols are given here: K, PUZ, PV, L33, L22, K equals to 1. This all I have taken from concrete frame design manual. So now first we have to determine whether our column is slender or not, and if our column is slender, using these formulas we have to determine the additional moments. To determine the column slenderness, whether it is a short column or a long column, I have prepared an short Excel sheet. Let us go through that first. Here I have prepared an Excel sheet for checking the slenderness of columns. And what is the slenderness? What is the formula for slenderness? Our formula for slenderness is effective length of column divided by radius of gyration. This is our formula for slenderness. Now in case of columns, our columns are solid sections, so we can change the formula for slenderness to effective length by D, where the D is the depth of cross section of column about which the column is likely to buckle. That means the value of D gives us the least lateral dimension of the column. So our formula for slenderness ratio is effective length of the column divided by the least lateral dimension of column. Now, if the value of this slenderness ratio comes out to be less than 12, then our columns are short columns, and then we don't have to determine the additional moments due to slenderness. But if the value of this effective length divided by least lateral dimension comes out to be greater than 12, then our columns are slender columns, and these slender columns generally fail suddenly at relatively low compressive loads due to buckling. Our short columns fail after reaching the ultimate load carrying capacity, while our slender columns generally fail suddenly at relatively low compressive loads. So we first have to determine whether our columns are slender or short columns. So in Annex E of IS 456 code, we have the procedure to determine the effective length of column. We chose our sample column to be at grade 5 in ETABS. And what is the stiffness, or what? First, let us go to ETABS. Let me cancel this. We see that in this column here, there are 3 beams being inserted into these columns. There are 2 beams in the x direction, this beam here and this beam here, and there is 1 beam in the y direction, this beam here. So for this sample column, at its one joint, there are 3 beams being inserted into these columns, 2 in the x direction and 1 in the y direction. While for another joint which lies on the base of this column, the joint is fixed. So what IS code says is that the effective length of these columns is based on the beam elements that is being inserted into this column. So how do we check for that is, let us go back to my Excel sheet. There are 3 beams being inserted into those columns, and there is our column. The size of our beams is written here, and the size of our columns. The length of our beam, you have to generate this property from ETABS. You have to look at this property from ETABS and put the value here. So we put here the length of column and here the length of beam. here length of beam and here length of column. Then we calculate the moment of inertia BdQ by 12 or second moment of area. So we calculate the moment of inertia from the formula BdQ by 12, and then we determine stiffness factor. The value of stiffness factor is given as the moment of inertia divided by the length. The moment of inertia divided by the length. So for each beam that is running through the column and for the column itself, we find the stiffness factor. Now, designing columns of all stories as sway columns, we use chart for effective length ratios for a frame without restraint against sway. That is, in IS 456 NXE there are two graphs. If you can see here, there is one graph for sway frames and there is another graph for non-sway frames. So we suppose that our columns of all stories are sway columns. That means our columns will deflect to the lateral side because we have lateral earthquake force. So we suppose that all of our columns are sway columns, and we use the graph for sway columns to find effective length ratios. And let us see here first our center to center length of column, that is our floor height, is 2850 millimeter. Our depth of beam is 350 mm. So unsupported length of ground floor column is L minus D. 2850 minus 350 is 2500 mm. And how do we find this value of unsupported length? In IS 456 clause 25.1.3, if you see here, we have the codal provision to calculate the unsupported length. The unsupported length L of a compression member shall be taken as the clear distance between end restraints, except that if you look at number B, it says that in beam and slab connection, it shall be the clear distance between the floor and the underside of the shallower beam. Since the depth of our beam, all the beams are the same, we have the depth is 350 mm. So our unsupported length of the column will be the distance between the floor and the underside of the beam. Of that beam, of which beam? Of shallower beam framing into the columns in each direction at the next higher floor level. So if this is our underside of the beam and we have column here, suppose this is our slab, this is our beam, and this is our column, this is the lower floor level. So we have that our floor to floor height is, this is 2850 meter, but our unsupported length will be from here to here. Let me draw this again. I will just erase this. If this is our column and beam connection, we have from here to here floor height is 2850 meter and the depth of beam is 350 meter. So our unsupported length means this free length of the column will be 2850 minus 350 is 2500 millimeter, that is 2.5 meter. So after calculating the unsupported length, I have here one table, and if you see it from NXE, if you see it E1 section, what does it say is that in the absence of more exact analysis, the effective length of columns in framed structure may be obtained from the ratio of effective length to unsupported length given in figure 26. When relative displacement of the ends of the column is prevented, and in figure 26 when relative lateral displacement of the ends is not prevented. That is, we have two graphs for two cases of either sway frames or non-sway frames. Sway frame means when the relative transverse displacement between the upper and lower ends of the column is not prevented. But when the relative transverse displacement between the upper and lower ends of a column is prevented, we call that frame to be braced against the side sway. But when that displacement is not prevented, we call the frame to be unbraced against side sway. And we have two different graphs for these two different conditions, but we take the graph for sway frames by considering that all our frames in our building is sway. So let us go to my table itself. Here first we check along the x direction and we check along the y direction. Column is the same. Now our unsupported length will be 2500 mm from here. 2500 mm. Stiffness factor for column we take from our table above. We calculated our stiffness factor here for column this and for 3 beams this. So our stiffness factor for columns is this, and our stiffness factor for beams will be now. In x direction we have 2 beams framing into this column from one side here and from one side here in x direction. So we add the stiffness factor for those 2 beams B1 and B2 from table above, and then we calculate here. For in y direction we only have 1 beam framing into this column. Since our column was at the edge, we have only 1 beam framing into the y direction. That stiffness factor we write here. Now summation of stiffness factor for columns, we take this KCU into 2, KCU into 2. Summation of stiffness factor for beams, we write whatever we have got here. Now we have to calculate this value of beta. The value of beta is summation of stiffness factor for column divided by summation of stiffness factor for column and beams. At the top, that means our column is, we have selected a column of the ground floor. Our column is fixed at the base and we have some beams framing into the columns at the top. So at the top, our beta top will be summation of KCU, this divided by this, we get 0.67, and for y direction we get 0.81. While at the bottom, since this end is fixed, we suppose that our stiffness factor for beams is infinite at the base. For that we get beta at bottom to be 0, since this infinite value will be at the denominator. Now after finding these values, you have to find the value of L effective by L from graph, either from this graph, or we also have formula for this graph which is here. So it might be easy also to calculate, because we have already calculated the value of beta 1 and beta 2. That is, beta 1 means beta top, beta 2 means beta bottom. So using this formula we can find the value of K, or we can find the value of L effective by L, since we know that effective length means the value of K into unsupported length. So K means effective length by unsupported length, which we get if we use this formula. Beta 1 means beta top and beta 2 means beta bottom. We get 1.37 and 1.54. Now we have the value of L effective by L. We have the value of L also in this column here. We can use these two values to get the value of effective length. 1.37 into 2500, 1.54 into 2500. Now we have our value of D here, 350. So finally our formula for the slenderness ratio was effective length by least lateral dimension. That is, if we do this division, L effective by D, we get 9.75 in first case and 11.02 in second case. Now since both of our columns are short, because our slenderness value is less than 12, we design our columns as short columns. From this calculation we got that our columns were short columns, so we don't have to check for additional moments due to slenderness. Using this process, which is stated in Annex E of IS code, we determined whether our column was short column or slender column. Since our column came out to be short, we don't have to design for additional moments. So let me go back to my presentation. You can see I have again posted a screenshot of another table from that our column design data. We see that our additional moment is 0. Our length is 2500 mm, which is our unsupported length. Our additional moment is 0. So in this way, we calculated this short column type. That means we calculated the slenderness ratio of these columns. This screenshot I have posted from my Excel, and we determined whether our column was short or slender. So finally, this is an example of the 3D interaction surface. Using this 3D interaction surface, now our software will check for capacity ratio. As a measure of the stress condition of the column, a capacity ratio is calculated. The capacity ratio is basically a factor that gives an indication of the stress condition of the column with respect to the capacity of the column. Before entering the interaction diagram to check the column capacity, the final moments are evaluated as outlined in our previous slides, and then this value of points is plotted in the interaction space, which is the value of this L. And we extend this OL line, which passes through the origin, up to this point C, which lies on our interaction surfaces here. And our capacity ratio now will be OL by OC. OL, which is the line from origin to the interaction surface. Sorry, OC is that line, and then OL line means the line from origin to the values of our forces. And capacity ratio is given by OL by OC. If OL equals to OC, capacity ratio is 1, then the column is stressed to capacity. If capacity ratio is less than 1, the point lies within this interaction volume and our column capacity is adequate. But if the capacity ratio is greater than 1, our columns are overstressed, and then we have to change the cross section and then calculate the capacity ratio again. And finally, the software calculates the reinforcing area. In our design of columns, the reinforcing area is not defined in the present or at the beginning. So the program computes the reinforcement that will give a column capacity ratio equal to utilization factor limit, which is 0.95 by default. For the maximum utilization factor limit, that is 0.95, the column gives us the capacity or the reinforcing area of that column. So in this way, the design of our column is complete. Now we have to go through the shear design of our columns. The shear design of our columns we will look in our upcoming lecture. So this brings us to the end of this presentation. We will meet again soon. Thank you.